I'm Meg Evans, Managing Editor of Spectroscopy, and I'm here today with Rohit Bhargava of the University of Illinois. Rohit, thank you for joining us today.
Thank you, Meg. Pleasure to be here.
How did you discover that vibrational spectroscopic imaging is not as simple as first believed?
When we first started doing infrared spectroscopic imaging, it was believed that the data that we got were a simple combination of microscopy and spectroscopy. So what you would record would be an image, and every pixel in that image would have a spectrum that would be identical to the spectrum of the material if you were to measure it in a conventional spectrometer. Even in the first studies, we saw evidence that this was not the case. In fact, one of the first papers I published in 1998 demonstrated that actually there are spectral distortions that arise from a mismatch of refractive index. So we simply switched the refractive index in the same materials, same structure, and we saw that the spectra changed. But at that time, we weren't as much focused on understanding the effects of structure on spectra because it was a very exciting time. We had just obtained the first IR images. Technology was very rapidly moving forward. So for a number of years after that, that aspect was sort of pushed to the background as we focused more on applications and exciting developments in instrumentation. So understanding these effects was always sort of the back of the mind, but never front and center. Then I came here to Illinois in 2005 and started thinking about those effects that we'd seen many years ago again. I started searching for some theory that might be applicable to this case, and we found that actually no theory existed to describe IR microscopy. So instead of focusing back again on these distortions or the complexities introduced by measuring both structure and spectra at the same time, we actually started focusing on very trivial aspects and trying to understand whether this effect really was significant, especially in the samples that we were seeing at that time, which were cells and tissues. And lo and behold, we found that, yes, there are significant changes introduced in the spectrum. Simply by changing substrates on which the samples are sitting, or changing slightly the dimensions of the sample, or changing the optics in the microscope. And then we were convinced that actually understanding all these effects and understanding the effect of structure, particularly of your sample composition on the recorded data, meant that we had to start from very basic level, from the fundamentals of this technique. So in about 2006 or 2007, roughly at the end of 2006 onwards, we started thinking about formulating a theory to describe all aspects of the measurement process, how light propagates from the source through the instrument, through a microscope, interacts with the sample, and then gets detected finally. But the work really took off when I started collaborating with two of my colleagues here, Scott Carney, who was a physicist, a theoretician in the electrical engineering department here, and a postdoc who was working in my group at that time, Bryn Davis. So we worked for about 2 to 3 years trying to understand the theory and formulating a complete picture from fundamentals to actually validate with the data that we were recording. And the first of these papers were submitted in 2010 and 2011. And there's a series of papers in analytical chemistry that now describe in full detail from Maxwell's equations to the images that you actually get without any empirical constants, without any adjustments. And the theory is sort of complete in that respect. Only after this did we actually start going back to the previous questions and start quantifying these effects that we were seeing very early on. And it's now become clear that we can predict what will happen if we put specific samples in. And just by changing samples, by changing optics, we'll start to get different data. So the true import or the true complexity of this imaging technique did not really become clear until just a few years ago. And now it's abundantly clear that we need to do a lot more work because the technology is not as simple as we first thought.
What was the most challenging part of conducting this research?
I think the most challenging part was at the same time most exciting as well. So when we started trying to look at the theory and trying to understand how predictions would perhaps relate to experiments, there was very little to go on. There wasn't a whole lot of work done on some aspects of understanding data in a microscope over many years. There was no previous theory on IR microscopy. Theories that have been developed for other forms of microscopy did not readily translate to IR microscopy because we were in a different regime. So to give you an example, most spectroscopists did not think of scattering too much in their calculations. In optical microscopy, one doesn't think of absorption too much but focuses on scattering. So there isn't a theory that completely describes IR microscopy. And finding your way without guidance was challenging in the beginning. But then we laid down some markers in terms of it had to agree with experiments, it had to be rigorous. We did not want any adjustable parameters. We did not want any sort of empirical constants in our process. So systematically, we could overcome most of the challenges. The biggest challenge was that there just wasn't anything to go on.
How do you think the theoretical understanding of light propagation will advance the field?
Well, I think this understanding and accounting for this understanding in all experiments and design of instruments will become absolutely central to the field. I think there are 4 reasons, perhaps, where this will make inroads into the field. First and foremost, I think it puts our field of infrared spectroscopic imaging on a firm theoretical foundation. So every technology needs some basic understanding to fall back on, and this simply didn't exist. So we were always falling back on conventional spectroscopy, and really the focus on the theory and understanding was primarily to understand spectra and relate spectra to chemistry. Now we recognize that the spectra in an imaging experiment cannot be decoupled from the structure. So not only do we have to understand spectra and their molecular origins, as have been done in infrared spectroscopy for decades, but we also have to understand now the relationship between structure, spectra, and molecular content all at the same time. Not only that, we also have to understand the interaction between the sample and the optics of the microscope to really understand the data that we record. So each aspect of this will be affected by this theory. I think it will allow for better design of instruments going forward. In fact, we have some ideas now on how we can better extract data simply by changing the instrument. We have good ideas now on what kind of lenses should we use, what combinations of lenses should we use to minimize effects that might arise from certain kinds of samples. It will also allow us to understand recorded data. So if you like to estimate the effect of sample structure on your recorded data, this kind of theory provides a very easy way to put in simply your structure and spectral properties of your samples and try to understand what you've actually recorded. But most importantly, I think this work forms the foundation of what will need to be done in the future, and that is namely to separate the chemical and the structural domains of your recorded data. So at this point, there is no separation of these 2 quantities. If you have the same material, but you have a different morphology or you have a different structure to your sample, you're going to record slightly different spectra. Do they become distorted to the point of being unidentifiable or being identified as something else? I think is still very sample dependent. But absolutely, there's no doubt that there is a coupling between structure and spectra. And how do we separate these 2 out going forward? Or at least understand the effect of one on the other will be a central topic in this field. So this theory really forms the foundation, and hopefully there will be newer approaches and work by other people also that will help resolve issues for specific cases, for specific setups going forward.
This concludes Part 1. Listen to Part 2 to hear Rohit Bhargava discuss how his work can affect disease diagnosis and progression, as well as the next steps in his research.